Okay, here we have some homework from 4.A.2, and it's 13.16 and 13.18 and 13.20 from the chain book. The first question asks us to go back to an example that we did in class and is in the book as well, example 13.2. If you remember in class, we found that the rate for that reaction was K F2 to the first power ClO2 to the first power. This was the very first one that we did initial rates method on. We also worked it out, so we found the K value, and it was 1.2 molarity to the minus 1 seconds to the minus 1. So then the question wanted to know what the rate would be if the F2 was 0.01 molar and the ClO2 was 0.02 molar. So simply plugging in K, F2, and ClO2, we get 2.4 times 10 to the minus 4 molarity per second. 13.18 is another initial rates method problem. It's a little more obscure because the various molarities and various experiments don't seem to have any particular order to them, but you can poke around and find some examples where one is held constant and the other is doubled. For example, if you look at experiment 2 and experiment 4, you'll see that the molarity of X is constant and the molarity of Y doubles. At the same time that the molarity of Y doubles, the rate doubles. So that means Y is first order, or to the first power. If you look at experiments 3 and 4, you find that the molarity of Y is constant, but the molarity of X, going from 3 to 4, is cut in half. At the same time the X is halved, the rate is quartered, or multiplied by 1/4, and so a half squared is 1/4, so that means X has an exponent of 2. So our rate law is rate equals K X squared Y, and the overall order, which is what they want in the question, is third order. Then in part B, we can calculate the rate constant K by taking the rate for the first experiment, 0.053 molarity per second, dividing by the molarities for the first experiment, which are 0.1 molar squared and 0.5 molar. Work out the math, you get 10.6 molarity to the minus 2 seconds to the minus 1. Plugging that in then for the rate law for 0.3 molar for X and 0.4 molar for Y, we get 10.6 times 0.3 squared times 0.4 is 0.38 molarity per second. Then we have 1320. We have a single reactant A, but we're looking at two scenarios, one where the rate law is first order, another where it's second order. We're given the rate and the molarity and asked to find K. So if the rate is 1.6 times 10 minus 2 molar per second, and the molarity is 0.35, when it's first order, dividing both sides by 0.35, we get that K equals 0.046 per second. If A is second order, then we have to square the 0.35 molar and divide it into both sides, in which case we get 0.13 molarity to the minus 1 seconds to the minus 1.